Welcome to the 14th lecture of Mathematics for Machine Learning. So, yesterday we covered one of the modules, which was matrix decomposition, right? And there we wanted to make matrices more friendly for computation, for analysis, for manipulation, right? You will be doing that again and again. तो वो सारी theory जो हमने पहले पढ़ी है, that doesn't help much. The matrix is too hard to handle, right? So, what we did yesterday is more of a start of computational or numerical solutions related to matrices, right? So, today we will continue within the linear algebra group, but this is kind of the last module in that group, which is vector calculus. You are already familiar quite a lot with calculus from your bachelor's and in master's, so we won't need to spend too much time on that. We'll just review some of the ideas that you already know, and maybe see them in terms of matrices that you may not have used as much. So, let's see why is there a need for that vector calculus. We had already seen when I motivated the mathematics part for this course that, for example, this is a neural network and the output is in terms of vectors. You can already see the things you have already covered, right? In here, the norms, the distance between what you want and what you are getting, yeah. But of course, now you want to minimize that distance and you want to find a quantifiable way to do that. So, often derivatives of these functions will be required, right? And that is what we are going to be looking at today, which is vector calculus. We will have very quick review of some of the basic concepts in there and extends them to vector cases, right? So, I think you know all of these things from before. So, what is a derivative? Different ways of defining, right? वो कहाँ से शुरू होता है, कभी function क्या कुछ. But I like to look at it as a study of sensitivity, right? So, what is the sensitivity we are studying in derivative? किस चीज़ की sensitivity study कर रहे होते हैं हम? Of the output to the input, right? So, often we are dealing with systems or operators, functions, जो मर्जी कह लें उसको, but this is effectively what's happening. There is some input, some independent parameters, some parameter in your control perhaps, and then there is an output, how the system responds to that input, to your what you give it. And what I want to know is, okay, how much is fx sensitive to changes in x, right? The sensitivity of my output to my input, yeah. And in that we might want to know, okay, we might want to find the change in output per unit change in input. That's one thing, yeah. Then we might also be interested in knowing how this sensitivity changes over the domain of the input, yeah. So, it's not like if I go from an input of 1 to input of 1.5, of course, there is going to be some change, yeah, there is some sensitivity. But what if I go from input of 10 to 10.5? Now, the amount of change I made is the same, but for some systems that change or the response or the sensitivity will depend on where I was I at 1 or was I at 10, yeah. So, the domain of x, where am I right now? Not just the amount of change I make, but where am I starting from? That may also be a factor. So, I might want to know that. For example, here fx equals 4x. This is one example of a simple system. So, going from 1 to 1.1, you can see that the output goes from 4 to 4.4. Going from 1 to 1.5 takes the output from 4 to 6, where because I made a bigger jump, so I got a bigger jump in the output. But the last one is interesting. I went from 10 to 10.1 and the output goes from 40 to 40.4. Yeah. So in this case, at least it seems the sensitivity, although it does depend on how much of a change I made, but it does not depend on where I was when I made that change. If I was at 1 and I added 0.1, I got an addition of 0.4. If I was at 10 and I added the same amount, I still got the same amount of change, right? This is what we of course recognize as linearity, right? So in this case, yes, the output depends on the amount of increase, but it does not depend on the actual original value of the input. What about this system now? What's the sensitivity of this system to the input? Its sensitivity is different from the previous one, right? Is for this system, you can see that if I go from 1 to 1.1, goes from 1 to 1.331, second one is fine. Look at the third one now. If I go from 10 to 10.1, the output goes from 1000 to 1030.301. Now, in the first and the third case, the amount of change I made is the same, right? So, of course, we expect the sensitivity to depend on how much change I make. But then in many functions, the sensitivity also depends on where I was when I in the domain of x when I made that change. So it means this can itself be a function of x. This sensitivity is not just how much delta x there is, it also depends on x plus delta x, right? So bringing those things together, knowing such details helps me know the sensitivity of the system to the input. But why do I want to know that? क्यों जानना चाहते हैं हम, right? Sensitivity उसकी prediction कर सकें, manipulate कर सकें, control कर सकें, to plan. That's the whole idea, right? So this may give me a quantifiable way of how much change in the input I need to make. जब मुझे पता है कि इस तरह behave करेगा, then I can know, okay, this much change in input from this point. If input was at 10, I need to make this much change. If input was originally at 1, I need to make this much change to make the output react in a certain way, right? So this is all about manipulating the behavior of the output, and we can quantify that, and that is where your derivative comes in, right? It's basically a quantifiable way to tune parameters. So in machine learning, for instance, it's often in a way the input in our control are the model parameters, right? So what we want to find out is, this is the question, how should I tune these parameters? क्योंकि आपके weights होंगे, biases होंगे, then there are hyperparameters जो हम इस तरह calculus से tune नहीं करते, often we just play with them, increase the number of layers, decrease the number of layers, right? But these parameters we deal with, the weights, the biases, the cost function, the activation function, those we deal with in a quantifiable way, exact derivatives वगैरह के ज़रिए, right? So so here's the formal definition, you know where things start, right? In general जब हम बात करते हैं derivative की, so you have a function y equals fx shown in orange, right? Now this is the function whose sensitivity to x I want to know, right? And the tool we have is, okay, I say, well, if I was at x naught, remember in general, as we saw in the case of x cube, in general it's not just delta x that will matter, it's also x naught. So we have to keep that here. So if I start at x naught and I change my input ever so little by delta x, and make it x naught plus delta x, the output, as you can see, will be f x naught plus delta x, whatever that function now comes out to, right? Which you can write as delta y is the change here. This thing forms a secant line cutting the curve in 2 points, right? Now the question we ask ourselves that leads to differential calculus basically is that what happens as this delta x approaches 0, right, as I keep making delta x smaller. Yeah, what will happen? So, firstly we recognize that delta y over delta x is basically the slope of the secant line. It is the tangent of the angle that this secant line makes with the x axis phi, right. That is of course fine, but then as we apply the limit, and if that limit exists, we call that the derivative of this function at that point, right. Remember उस point पे क्यों ज़रूरी है? As I said, it's not just the amount of change, but also where you are. Linear system में नहीं फर्क पड़ेगा, but in general it will vary, so we have to keep that in mind. That's why the derivative is itself a function, right. So, you calculate it at different values like this. Yeah. Now, there is another perspective here. The perspective was decreasing delta x, right. The other perspective is what happens as q, the second point, approaches p, right, this point from left and from right. So, you can imagine as q approaches p from the right, the secant lines are changing and eventually they turn into a tangent. Similarly, from the other end you can start seeing that they approach the, in this case they approach the same tangent, right. If we write that, then we are saying okay, as delta x goes to 0, q approaches p and the tangent of the secant approaches the tangent of the tangent right, or the angle of that tangent theta. This is an alternate way of looking at it, and if we see the two together, right, these two ways together, we come to the conclusion that the value of a derivative at any point of a curve is equal to the slope of line drawn tangent to the curve at that point, right. Actually this issue of the secant was what Leibniz was trying to solve when he came up with differential calculus, the co-inventor of, I think Newton integral calculus की तरफ से आया था वो summations, and this guy came from the differential side. So he was actually trying to answer this question. Yeah, तो अगर आप पहले देख लेते सवाल शायद आप भी इन्वेंट कर लेते. बहरहाल, so we know this definition, it's fine. As I already said, in general a derivative itself is a function, right. Why does it have to be a function? We already saw that it's not just how much change you make, but where were you when you made that change will also affect the sensitivity in general. So it tells us how the rate of change changes over the range of the input, right. For example, in this case the blue color is the function, the principal square root, and the orange one shows the rate of change, and notice that the rate of change is not constant, right. The rate of change itself is a function. Here the function is changing much faster, right. So the rate of change is getting high values, but as you approach this part the rate of change slows down, right. So you can see the rate of change is slowing down to some steady value. Yeah. In this case what is going on? Is the rate of change increasing, decreasing, or what? Rate of change is constant नहीं है. Constant के लिए you will need a straight line. It confusing होता है. You are thinking of the slope. Yeah, the slope is fixed, but slope fixed means for derivative it means that it's constantly growing. Yeah. So here the rate of change is high, though negative. Slope negative है. Yeah, but high. Here the rate of change is high. Here exactly at 1 the rate of change becomes 0, and then it keeps, so it grows in positive values here, and it is growing in negative values here, right. So the rate of change is also changing. It's a function of x. That's why we write it like that. So Of course, you are familiar with using derivatives. पहला काम ही हम वही करते हैं फ़ौरन. Yeah. So we go and try to find optimal points. Now we know that this is the derivative again. As I said, the derivative is also a function over the range. Yeah. So we recognize that there are certain points where this derivative becomes 0. We call them we realize that they have to be special points, so they are the optima. We know for the simple cases that if it's increasing on the left and decreasing on the right and 0 in the middle, it looks like this thing and that thing. So then we bring in second derivative, which is now the rate of change of the rate of change. Right. So it's the slope of the slope. Yeah. And why do we need that? Because the derivative itself can be a bit confusing. It's on the left it's so much, on the right it's like this, but the second derivative, if you look at that, so this is drawing the first derivative. Yeah, this is the slope, first derivative. Now if it's concaved upwards, you recognize that if you go from left to right over a upward concave, right, इसकी direction ऊपर की तरफ, then the slope is basically increasing, right. Here it's negative but becoming less negative, so increasing in that sense. Yeah. So it's the slope is increasing, whereas for the concave downward case the slope would be decreasing, right, going from left to right. Of course से आगे जाके फिर दोबारा change होना शुरू हो जाएगा, but we are only interested in that curved part. Yeah. So that of course that means if we study the slope of the slope now, अब हमने we are not looking at the curve itself, we are looking at the slope of these pink arrows. The pink arrows are the derivatives. So we are looking at the slope of the slope function, right. And if we look at that, of course there is inflection point thing. So with that we can now, famously we know this, yeah, we then identify. First you find them, you list them, then you try to identify them. Is it a minimum, is it a maximum, can you justify it being a global or not, वो फिर आगे मज़ीद optimization theory में आते जाएंगे. So you already know these things, just a formal definition. Then this is called the difference quotient, जहाँ से कहानी start होती है, is the secant की जो angle था, जो slope थी. When you put your limit on it, and if the limit exists, दोनों side से 0 plus 0 minus, right, then and it's the same, then you get what we call the derivative. Then you are familiar with some lots of rules. I think आगे rules ही rules होते हैं वो लगाते जाओ, right. So product of two function, quotient of two function, sum rule, chain rule, the one that we are most commonly using in machine learning, chain rule, right. So because it involves composition of functions, and deep learning especially is all about composition of function. हर layer एक composition है, right. So you are familiar with all these. G of f of x prime is g prime f x times f prime x. So what is this formula saying, this one? Can you explain this in words? Right. So basically you want to see actually that how g changes, how sensitive is g to x. The derivative is respect to x. F का हमारे साथ ताल्लुक नहीं है, but we are forced to work with it. Why? Because we don't have direct access to x. We have access to x through f. Then to find out how sensitive g is to x, one way is to say, okay, how sensitive is f to x, and then how sensitive is g to f. ठीक है, that is the chain rule. वही लिखा हुआ है. पहला right पे है, how sensitive is x f to x, f prime x, and then how sensitive is g to f, right. So अब आप इसको जितना मर्जी लगाते जाएं, g x y multiple compositions पे. So multi-sensitivity. Of course, what I showed you so far is a single variable case, right? So, but in general what we are dealing with are for systems that depend on multiple variables, and I may want to know, okay, how sensitive is the input to is the output to each input, for example here, right. So, of course, I could check the sensitivity of the function with respect to w while keeping the other one constant, क्योंकि सारी तो इकट्ठी चेक नहीं हो सकती, मुश्किल है, you will not know what happened. So that is the age old way troubleshoot करते हैं ना आप वो चीज़ों को. So you minimize the variables, एक variable at a time, right. So पहले दोस्तों को कॉल करते हैं कि आपकी बिजली आ रही कि नहीं आ रही, right. तो पहले तो एक वेरिएबल ये निकाल देते हैं कि सबका मसला है तो बस कुछ नहीं होता, right. So in this case you will fix all the others and just see one, right, the sensitivity of your function to one of the inputs. In this case it turns out 3w, and then you check the sensitivity of your function to the other input while keeping the first one constant, turns out to be 2. Now this insight can also be achieved exactly by taking derivative of fwx with respect to w, treating as x as a constant, and then taking derivative of with respect to x, treating w as a fixed constant, and this we call partial derivative. Naturally they come up, yeah, the partial derivatives. So for this case the two partial derivatives are 3w and 2, yeah. Now we often like to put them in a vector, yeah. इस vector को क्या कहते हैं हम? Gradient, yeah. So we call this vector a gradient, we denote it by this nabla sign, yeah. So delta वो था और ये उल्टा gradient, yeah. So it is a vector which brings us back to linear algebra, right. So what does each element of the gradient represent is the partial derivative of the multivariate function with respect to one variable, that is splits the function sensitivities according to the variable. So उसकी values पढ़ते जाएं. What is the sensitivity of my function to variable w, variable 1, here it is. What's the sensitivity to variable 2, here it is. हर एक की sensitivity is put in a vector form. What's the geometric interpretation? You are familiar with that. Basically if this is the surface, 3D surface represented by fx y, yeah. So it's a function of two variables. Then what you're essentially doing when you take the partial with respect to one of them is that you say, okay, if I'm interested in this point can be reached two ways, can be reached on this curve or on this curve, right. So मतलब और curves पे भी वैसे आ सकते हैं आप, लेकिन still it's enough to look at it here. So I might be saying, okay, do I take this slope or do I take this slope like this, yeah. Luckily we can take both of them. One of them is actually where you fixed x, एक slice निकाल लिया आपने, एक curve आ गया, yeah. So that is the partial with respect to x, whereas in the other one you fix y and you get the partial with respect to y. So this is what you are doing. Again just to demonstrate, same thing, you have a surface fxy, you can cut it in two ways, along x or along y. So it's the same point, yeah, x naught y naught, it's the same point, but there are two tangents now, one along one curve and the other, and any variables के against हमें sensitivity देखनी है. So we got both the sensitivities. There is your formal definition. Before we defined basically, if you remember, fx1 plus h, ये नहीं था, yeah. Now this is the new thing here, that keep them fixed, don't change them. The only change is in this guy h, where xn change xn, जिसका partial निकालना है उसको change करें, limit लगाएं, कोई बात आ जाएगी, लेकिन you have to fix the others. So it's a very simple way. Basically आप उसके अंदर से वही simple slices निकाल रहे हैं, and then applying the very basic definition of derivative, right. So then you have the product rule, sum rule for partials. Chain rule for composition of single variable function, again same thing. The sensitivity of, you want to find the sensitivity of g to x, right. So, you find the sensitivity of f to x and then the sensitivity of g to f, right. Chain rule for multivariate composite function. So, now what is the difference between the first and the second one? In the second one, f now is a function of two variables and they themselves are function of another variable, right. इधर जो है ये दोनों एक ही के function, एक ही variable के दोनों function, right. Here f is a function of two variables and those two are then separately functions of. So, the chain rule extends naturally, total आ जाता है वो, ठीक है, you know this very well. Chain rule and gradient of a composite function of multivariate. अब क्या हुआ है पिछले से? First we had fx gx, then we had or f of g of x, right. Then we had f of x1 and x2, but then x1 and x2 are functions of one variable. But what if x1 and x2 are now functions of more than one variable, right. तो चीज़ें और complicate हो जाती हैं, general होती जाती हैं. Then you have, of course, you will first do the partial respect to s, then the partial respect to t. Within each you apply exactly the same rule that you saw there. So, you have that, and the gradient in that case basically you can calculate, right, using standard methods. So, gradient as a vector field, we often like to plot the gradient. Gradient है तो vector ना, अब ये vector भी है और just like the derivative it depends on the choice of x and y, right. So, ये पूरा एक function है. So, you can कई vectors उससे आप निकाल सकते हैं. For example, in this case we found the gradient to be 3w2, right. तो जो w cube plus क्या था 2x, yeah, was it that? Okay. तो फिर 3w square होना चाहिए ना, वो गलत हो गया वो. Yeah, I think I typed it wrong. Anyway, so let's say we had something like this, yeah. In that case you would have the gradient, you can calculate it on all the points wx. Here I am showing you 3 points, right. Now, each point leads to a vector, right. Now, what if I plot these vectors? Starting point इनका क्या होगा? For each of these vectors, the starting point is where they were calculated, right. So, इनका origin, इसका origin ये है, इस vector का origin ये है और इसका ये है. If I do that, I get a vector field, right. I am only showing 3, but of course you could show many more, and here you have 2 comma 3. So, 2 comma 3 here it starts and it goes this way. What are these arrows showing us? क्या show कर रहे हैं? Of course they are representing the gradient, but what do they mean for us, right? Remember sensitivity, change, how much change, yeah. So, this vector field shows us where the most change is expected and in which direction, right. So, at 2 3 w and x 2 3 the arrow देखें बहुत बड़ा है, much sharper change is expected, and in which direction? More heavily tilted towards w. W is more dominant, which makes sense because it's w cube plus 2x है ना, तो वो cube के साथ जा रहा है, yeah. So, gradient as a vector field, so it helps us find direction of most rapid change, which is steepest ascent or steeper descent, heavily used in optimization, machine learning. So, this is what it does basically, जो मैंने अभी plot किया आपके लिए पहले. So, you could plot it in often we plot the gradient on the surface, on the function itself, but you could also plot it in the variables x, y. This is plotted on f x, y, right. But in either case, it is pointing you towards the sharpest from that point, which way you should go to get the sharpest change. Here I give you some example. This is a nice website, interactive. You can make your own functions and study their vector fields. So I tried this a toy example where I fixed y, so the function does not depend on y basically. Yeah, if you plot it now in 3D, then y does not play a role in that. In that case, if you look at the vector field now, what is it saying? Is your vector field x? Notice all the vectors arrows are in the x direction. They are saying there is no point moving along y, right? Okay, if you move along y, you are if you are here and you move along y, nothing is changing. Wherever you are, कोई एक point ले लें. If you move along y, nothing changes. The only reason it changed from here to here is because you moved along x, right? So the arrows are telling you, the vector field is telling you that to get change, maximum changes, is along x. Not only that, what else are they telling? Notice that initially they are small, then they are bigger, and then even bigger, क्योंकि वो along x square के साथ ये function है, right? So the rate of change is also increasing, right? So higher जो आप जाते जाएंगे, steeper वो होता जाता, yeah. So yeah, we see that. Same thing I repeat for the other way. I fix x, x का आप कोई उस पे रोल नहीं है. Now it's showing me that all the changes you want to see should be by moving along y, yeah. And in this case, which is very commonly we see, दोनों में अब आप move कर सकते हैं, right? So this is the just for easy understanding of vector fields. So the general formulation of the gradient, if f is a function Rn to R, multivariable, single valued, ऐसे ही है ना, Rn से R में जा रहा है ना, scalar assign कर रहा है n values को, so it takes multiple values but gives you single output. In that case, we have already defined the gradient. Just collect all the partials in a vector and you have that, right? Now let's make it take it to the next level, which is not just it's multi-valued, Rn say Rm, so it gives you multiple outputs. If you remember, in a function we did not allow one to many mappings, but we did talk about multi-valued functions as a function where you get multiple values, but they are kept separately, like in a vector. As long as you keep them separately, you are allowed. You could put them in I, j, k direction, right? वो जो हम करते हैं, और put them in a vector, जितनी मर्जी directions में डाल दें, आपस में वो आप mix नहीं कर रहे उनको उसका, then you are allowed. That is called the multi-valued function, right? So now things get the most general they can get basically, which is now you can take many inputs and you can give many outputs. Then our original question also expands. Now we want to know the sensitivity of each of the outputs to each of the inputs, right? So अब vector से भी काम नहीं चलेगा, so we'll have to go to a matrix, right? So we'll have to go from gradient vector to Jacobian matrix, right? And here is your Jacobian matrix. Each row is your original gradient vector, right? So here if you move along the rows, you are looking at one of the function's outputs, f1, or the function's value, function's subfunction, with respect to all the variables. That's one gradient, right? Then the mth, because it's ये कहाँ से आ रहे हैं, ये वाली rows, columns, ये जो these are coming from multi-valued. अगर वो single valued होगा, it will collapse to just this thing which was the gradient, राइट. सो ग्रेडियंट्स को हमने रो वाइज रख दिया है. सो वी गेट द Jacobian matrix. So here's the formal definition of the Jacobian matrix. Again, nothing special, limit x goes to 0, the variable you are interested in and the function, sub function within the function that you are interested in. So each one, partial f with xi, partial f with, you can find with each one of the variables. So basically you collect all the sensitivities, all the pairs of sen. Now what does the Jacobian matrix represent? Right, gradients hain ye, yeah, of course, but at each point where function is differentiable you can think of the Jacobian as describing the amount of stretching, rotating or transforming that the function imposes locally near this point, right. Derivative में भी यही कह रहे हैं ना आप single function की, it's at that point how much change you expect is able to change. Yeah. So in case of this guy, of course it's in higher dimensions. So you are familiar with linear transformation and non-linear transformation, जो हम already linear algebra. So if this is the space, this is a linear transformation of the space carried out by a simple matrix multiplication, right. वो हम करते आ रहे हैं ना, yeah, it's still linear. But there could be non-linear, which we did not study. हम linear algebra पढ़ते रहे, right. So that does not restrict too much our linear algebra, as we will see, क्योंकि locally फिर वो linear approximations बन जाते. So this is a non-linear function. So instead of a simple matrix multiplication, this is non-linear functions applied to our inputs. So the space has now, yeah. So where does Jacobian come in? Interestingly, the Jacobian acts as a locally linear approximator. So if the transformation were linear to begin with, जैसे ये यहाँ पे first case, yeah, if the transformation is linear already, then the Jacobian is simply representing the effect of that transformation. Yeah. But if the transformation was non-linear, then Jacobian represents the locally closest linear transformation, उसको approximate करता है, ठीक है. और this is not something very strange. Derivative में भी तो यही नहीं होता. In the derivative for a simple function f(x), ये एक लाइन में अगर आपको दूँ, इसका डेरिवेटिव क्या होगा, राइट, कांस्टेंट होगा, यानी इट विल गिव मी दिस स्लोप एग्जैक्टली, स्लोप बता देगा वो क्या है इसकी, राइट. बट इफ आई गिव यू अ कर्व, देन एट ईच पॉइंट it approximates it with a small line, right, locally linear approximation देता है. So Jacobian is gonna do the same thing. In that way it's a very powerful tool. It locally linearizes the transformation if it's non-linear. अगर transformation linear ही हो फिर तो ये exact value देता है, जैसे इस case में approximate तो नहीं angle देते ना, exact ही देते हैं हम. Yeah. So in that sense we can, since we like linear transformations from vector algebra, so we try to see it alternate derivation, or the derivation of the Jacobian is that you see, okay, there was something du dv and it was nonlinear transformed, but if you look at it in macroscopically, very small section में देखेंगे so it can be represented as a very small linear transformation. We will call that dx dy. So du dv has now become dx dy, and if you write that out as a linear, if you say, okay, there is a multiplier j, right, that was a linear multiplier, that is a b c d. If you multiply that out, now this second जो lines लिखी हैं dx equals a du plus, if you compare that to the chain rule we already looked at, this one, yeah, if you compare that, what does j come out to be? exactly the definition of Jacobian, right? So for the you may say two variable case banaya, right? So it is actually justified to call then Jacobian a linear transformer, yeah, a linear transformation leads to the same one. The determinant of the Jacobian in that sense also is a very useful idea. It gives you the factor by which the area is changing. Okay. So, it finds the local linear approximation of the change, and the determinant of J gives you how much area has changed from this to going to this. Now, the actual change might be different. Okay, if the transformation was actually non-linear, this thing won't be linear, it will be कुछ third dimension में भी वो curves होगा, but we find the closest match to it, right? And the smaller you make that region, the more accurate, इसीलिए वो tangent का भी तभी फायदा होता है ना सारा. So in summary, this is what happens. You had a space, there was a non-linear transformation on it. अब जो actual transformation हुई है वो कौन सी है? This red one. देख रहे हैं? This is non-linear. Now the Jacobian cannot find that. Yeah, what it can find, okay, what's the closest in area to this which is still linear? वो ये. So the determinant gives you the ratio of the area of the original to the area of the closest linear approximation, not the original, but as they approach delta x and delta y, it becomes very accurate, right? So now we want to go to higher order derivatives. पीछे हम कहाँ गए थे? We increased variables basically, yeah. So we started with single variable, single value, right? Then we said multivariable but single value. Then we said multivariable and multivalued, and got Jacobian. Now we want to come back and say, okay, what about, we said we talk about the second derivative of a simple univariable function. So we want to write those generally now, higher order derivatives. So the case for multivariable Rn to R, we already saw that it was useful, higher order derivative was useful, so similarly it can be useful here, and there it is. Basically this is your Hessian, which is the collection of Jacobian में first derivatives पढ़े होते हैं, right? इसमें second derivative, if it's Rn to Rm, then you will have to deal with tensors. Okay, वो फिर एक अगली layer add हो जाएगी, but the principle remains the same. So Hessian is then what? The matrix comprising all second order partials of a multivariable function, right? If f is twice differentiable, then the Hessian is symmetric. Okay, then because partial square x2 x1 is the same as partial square x1 x2, right? So well known results. How are they related? ये बड़ा मजे का result है. Hessian is the transpose of the Jacobian of the gradient. ठीक है, सारे एक ही लाइन में आ जाते, समझ आ रहा है? It's the transpose of the Jacobian of the gradient. Okay, so what does the Hessian now represent? Just like वो हमने उस वक्त curvature के लिए use किया था ना second derivative. So इसी तरह यहाँ भी यही है. It's actually making the curvature of the function locally around a given point. So if you have these different points, then it's approximating them by a second degree polynomial. Yeah, so it's just giving you a guess, local guess of the curvature, convex up है और concave down है, concave up है, कैसे है, saddle point है. Yeah, so same thing. So how do we identify critical points? Simple function में तो था बड़ा maxima minima identify. इसमें the same thing extends to matrices now. Hessian is a matrix, so we'll have to talk about positive, definite, etc. So the test can be applied at any critical. We are assuming that you have found the critical points. Yeah. Now at those critical points Hessian may or may not be invertible, but if it is invertible, then you can apply this test, which is that if the Hessian is positive definite, which means all eigenvalues are positive. अब eigenvalues याद है पिछले दफा हमने करें, then we are talking about a local minimum. Yeah, if Hessian is negative definite, all eigenvalues are negative, then it's a local maximum. If Hessian has both positive and negative eigenvalues, mix आ गई eigenvalues, ठीक है, eigenvalues की power नज़र आ रही है आपको कितना वो useful चीज़ है, then it's a saddle point. Otherwise, test is inconclusive. Saddle point तो उसमें है positive and negative. I think what they mean by otherwise is zero eigenvalues की बात करें. राइट पर मैं इसमें ये सोच रहा हूँ कि इन्होंने ऑलरेडी सैडल पॉइंट का तो लिखा हुआ ना, थर्ड वन, राइट. सो अदर देन दैट क्या ऑप्शन हो सकता है जो यहाँ नहीं लिखा हुआ, फॉर विच द टेस्ट वुड बी इनकंक्लूसिव, यानी क्रिटिकल पॉइंट आप I think what will happen is what they are not covering are zero eigenvalues, and when there are zero eigenvalues, Hessian will not be invertible. If it's not invertible, you say your test is inconclusive. I cannot say anything, right? वो point ऐसा आ गया जहाँ पे वो हाँ. So helpful formula for vector calculus, ये आपके काम आएगा. Partial of a function of a matrix with respect to that matrix. Okay, so we have इस तरह की पूरी किताबें भी हैं, like they collect all these functions. They're very helpful. I've used them a lot in my PhD work. They are kind of shortcuts, otherwise it becomes a pain to do all that. Yeah. So let's this is the last thing here, a few last things which are the applications now. So हमने क्या क्या देख लिया, simple derivative, partial derivative, collect the partials in a gradient, collect the gradients in a Jacobian, and then if you want higher order gradients that becomes Hessian. तो वो हमने उसका सारा बस यही summary थी. Now we just want to look at their applications, for example least squares. So you have a linear model, y is phi, it's a matrix. This is a parameter vector, and what's in your, usually the data is here, and these are your neural network parameters, the weights and the biases, right? And this is the output they give together, and what's in your control is this guy. So you want to find what theta should I choose so that the difference between my desired output and what this model gives me is minimized. The Euclidean distance, perhaps we already saw that you could choose other distances depending on your problem, but this is the most common one. So this is called the least square loss function. So how do we find that? We want to find the partial of L single valued है, multi valued है? वैल्यू तो एक ही देता है, मल्टी वेरिएबल है, राइट, पर आउटपुट इसका एक ही स्केलर आता है, नॉर्म है ना. सो इट्स अ सिंगल वैल्यूड फंक्शन बट मल्टी वेरिएबल. या वो वेरिएबल्स उसमें थीटा हैं, जितने थीटा में जितने भी हैं n वेरिएबल्स. सो we can apply the, what we are interested in finding is this thing. Again, remember, what we want to know is the sensitivity of L to theta. If we quantify it exactly, we can try to find कि ये कहाँ minimum इसका आता है with respect to theta. So chain rule comes to the rescue. Why did we need to use the chain rule here? Because we have access to theta through E, right, through the error function. So in that sense, we want to be able to use this, and then we will have to apply the partial with respect to each of the elements, for example here. So now what are we doing? We are solving this thing one by one. Yeah. So we are trying to solve partial of L with E. Now when we are doing that, we don't need to bother about theta, right? We know that L was defined as the 2 norm of E. Now the 2 norm from our understanding is ETE. So the partial of L with E to ET, here you can make use of one of these results, something like this, or so you don't have to start over. Usually I used to have this 30 pages ka wo tha full of formulas like this, then I would just look for the one I need. Yeah, क्योंकि scratch से निकालना ज़रा headache होता है. So yeah, so partial और थोड़ी practice भी हो जाती है, फिर आपको समझ आना शुरू हो जाती है कि कैसे होता है. So it's 2ET, which makes sense because it's kind of a square, right? So then we are, of course, we need to solve this guy also, right? Partial of E with theta. Now partial of E with theta is minus phi. You can check that, yeah. So because if you look at it here, y minus phi theta, y तो आपके कंट्रोल में नहीं है, it's the desired output जो कि कोई fixed value है, तो उसका partial तो गया. Then phi theta का partial लेंगे तो of course it will be minus phi with respect to theta ले रहे हैं ना. So now if you put the two together, you get the partial of L with respect to theta. This is the point or this is where the minimum will occur, and if you solve this for what the minimum value is, आप बस वही लीस्ट स्क्वायर्स का रिजल्ट आ जाएगा, फाई टी फाई इनवर्स फाई, वो जो हम पहले ही निकाल चुके हैं, राइट. So another application, differentiation of matrix equations. Now you have a matrix equation, f is equal to ax, f is a vector, a is a matrix, and you want to find the derivative of f with respect to this guy. Interesting, right? So how you will do it? Again, वो जो मैंने function formulas दिखाए हैं वो, plus often we try to identify the elements in there, matrix के ना, okay, which element are we talking about? So like here we do see that, okay, this is df by dA can be seen as partial of f1 with a up to partial of fm with a. पहले थोड़ा split कर लेंगे उसको, right? Now each one we will see, okay, what is each function representing. अगर आप इसको matrix form में if you try to read it out, this is what it comes out to be, right? f में ये है ना, f1, f2 and so on, right? And that is made of ax, right? So you can already see, okay, a के पहली row multiplied by the column, right? So you can already get a pattern for f1. f1 is j is 1 to n because you have to go over all these guys, but the I is fixed. So f1 is a1 first row of a. So usually इसमें यही होता है. You are often trying to find the patterns of the sub functions ताकि फिर आप उसका derivative ले सकें, ठीक है? So once you do that, it becomes very obvious. अच्छा, once you write it like this, it becomes very obvious that the partial of fi with respect to a I q, I same row, different columns, yeah, will be x q which is from here. So x q, this allows to compute the partial derivative with respect to each one of them, and if k is not equal to I, 0 आ जाएंगे. Patterns तलाश करते हैं आप फिर, और then you keep going. Finally you have the partial of fi with respect to a is these zeros and then xt. This is just one of them, yeah. So then you have to basically put all of these together to form the full derivative. We also sometimes need to take the derivatives of special matrices. Now this is the gradient of matrix with respect to matrix. So the gradient of RTR with respect to R. Okay. So again अगर आप नोट करें तो it comes down to trying to identify कि कौन सी रो किस कॉलम के साथ मल्टीप्लाई होनी थी, क्या होना था और उनके आपस में रिलेशन क्या होगा. यूजली दे आर नो शॉर्टकट्स, ये काफ़ी बड़े 10-10 सफ़े बनते हैं ये सॉल्व करते हुए, राइट. So eventually you will find some patterns and you will have that. Back propagation, that's also a very important application of vector calculus that we heavily use in deep learning. We are dealing with heavily composited functions, right. So we want to know the sensitivity of y to x actually, हमें तो ये चाहिए ना, लेकिन x here is the parameters. So to do that we need to know the sensitivity of f1 to x, and then we need to know the sensitivity of f2 to x as manifested through f1x and so on. Luckily we have the chain rule, so we can expand that. This is what a simplified diagram of a neural network looks like. There is the input x, but that's not really in your control में नहीं है, it's something that's given. It's actually these a0, b0, a1, b1. These are the collection of the weights and the biases. These are in your control. Now they reach the final destination L, where you are able to tell if they were good or bad, right, through so many compositions. हर stage अपना function एक non, पहले वो linear multiplication को sum करती है, फिर उसके ऊपर activation function लगाती है जो कि non linear होता है, करते करते आप वहाँ तक पहुँचते हैं. So of course the first one f naught x, then fi is the sigma is the non-linear activation function, ReLU हो गया कोई और हो गया, right, and that depends on the weight parameters of the and the bias of the previous layer, right, and the function previous function fi minus 1. So these are the parameters, let's put them all in theta, they are in our control, and final cost function is here. Now we want to see the sensitivity of this cost function to theta ताकि हम उसको ट्यून कर सकें. But to get to that, वो अब theta आ रहा है fk में, but fk is inside fk minus 1, fk minus 1 is inside fk minus 2, वही heavily composited. But okay, we can just keep applying the chain rule. So we say okay, partial of L with theta k minus 1 is partial of fk with respect to last जो लगा था उस पर, right, with respect to theta k minus 1, and the partial of L with respect to fk. But then we could see okay, the things didn't start here, उससे भी पीछे एक layer थी, right, bring in that layer. So then we say okay, then partial of fk with respect to k minus 1 and fk minus 1 and the partial of fk minus 1 with theta k. इस तरह keep going all the way to the end. Yeah. So the general case is this one, where if you put theta equal to theta 0, you will get the whole thing, right. So basically this is what we call back propagation of error or back propagation, because it starts with the error function and keeps going backwards, giving you information about how much each of the sub function is sensitive to your selection of parameters, right. So homework for you is to read the general cousin of this guy called automatic differentiation. Back propagation is a special case of something called automatic. सुना हुआ इसका, यूज़ किया हुआ भी, बहरहाल उतना मुश्किल नहीं है, but it's a special case of that. In general for us back propagation is sufficient. So of course you are familiar with this application. Often शुरू में ही पढ़ा देते हैं हम कि using the local derivatives, वही locally linear करते जाएं, locally linear, तो you get a approximation of the, so I don't need to cover that in detail. Taylor series, this was Taylor polynomial, this is a Taylor series of the function. So for example, the more terms you add the more closer you are getting to this thing. So I had already said in one of the earliest lectures that Taylor series is also a universal approximator, right? Not a very useful one because the derivatives बहुत ज़्यादा मांगती है and requires your functions to be heavily differentiable. अगर हज़ारवीं टर्म्स चाहिए तो 1000 दफ़ा वो डिफरेंशिएबल हो अक्सर मुश्किल ही होता है, ठीक. So so it's good for analytical discussion. That's why the functions जिनकी ये exist करती है उनको हम क्या कहते हैं, analytic functions, right? But real data doesn't have to follow that. So इसलिए इसका इतना कोई use नहीं है. It's the Fourier approximator that is more useful for us because that looks at the universal global picture. ये देखता है local को, वो global को fit करता है. Taylor series of multivariate function, just like here for single variable ये ऐसे होती है, तो multivariable के लिए we replace the higher derivatives with the gradient, Hessian, उस अगले का नाम भी कोई होगा, d cube वगैरह, right? So locally linear approximation of a single variable function, well known, right? We know that. Linear approximation of a multivariate function, वहाँ आपने derivative था f prime x naught, now just replace it with gradient, right? Linear क्यों है ये, क्योंकि you stopped, basically you take the Taylor series but stop at the linear term, हाँ, constant plus first derivative. तो वो अगर वहाँ नहीं रुकना आपने, तो you could take the second order approximation, which is very common in numerical methods. Maybe आप कर रहे हो already optimization में, Newton type methods heavily use this one, right? So there they naturally go to the second order, which includes the Hessian then, right? So this is the last slide we have used in well known Newton's method में. For the single case we know that one. Sorry, left column है one dimensional, right? And the multi-dimensional is the right column. Similarities आपको नज़र आ रही होंगी. Second derivative is replaced by Hessian, first derivative is replaced by gradient, all that, right? So that's that. Let's take your questions.